What's geologically interesting about these cliff sides? First off is the color. What's the primary dominant color?
Red.
Red. What is red rock?
Sandstone.
No. Iron. It's rust.
Oh.
Those rocks are heavy in iron, right? Now what's interesting is you can actually see, especially like see this little bit over here of the rocks, like the yellow and whiter kind of rocks,
Yeah.
right? In tight layers, right? That's, you can see a little bit of that pattern over there right on top of, see it's like a big red streak and then brown, like a gray and then a little bit, right? So you can see that layer was there, right? What's interesting about this really deep red rock is it likely is extremely old, right? It likely came from very deep in Earth's core with the iron, which is very exciting. That's my current hypothesis.
Iron is an earth core.
Earth's core is made of iron.
How do we know that?
We know that, fascinatingly, from
Magnetic?
That's the first thing. We can tell from magnetic simulations of the Earth's magnetosphere. So we have satellites orbiting Earth that orbit Earth and measure Earth's magnetosphere, right? And from what they measure, we can see that. That's the one thing. The second thing, which is way more interesting, right, is we can tell the different densities by earthquakes. So if I have an earthquake here, right, and I'm on the globe, it sends shock waves into the ground, right? And then at every major material interface, there's a reflection of waves back. Think like optical waves, right? And so they can use essentially the geologic equivalent of Snell's law to determine the densities throughout. And then what's really interesting about that is that the Earth's core is so hot and so dense that it forms a shadow of the like if the earthquake is here and the core is here, there's an arc of the Earth that's shadowed and doesn't see any of the vibrations from that earthquake because it can't penetrate through the core.
What does the shadow have to do with it?
It helps us determine the density of the core, the size of it too, because you can use geometry to determine the size of the core based on the shadow it's casting and where it's not showing earthquake
Can you
vibrations.
calculate how far down it doesn't show an earthquake?
I know, but I have a point and I'm projecting a cone out against the sphere, and I can measure the surface area that didn't see vibrations from the earthquake and come back to measure the size of the sphere. It's a geometry problem. What do you think?